Okay, let's go ahead and get started. So good morning, evening, afternoon, everyone, depending on what time zone you're in, and thanks so much for joining us. Before we get started, I just want to remind everyone that we have the Q&A feature available. So if you have questions at any point, you can use that, and we'll have time for questions at the end. The closed captioning is also turned on for this webinar. Um, we also have a suggestion box that you can use to suggest future speakers in the series, and I'm going to put the link for that in the chat. We're always looking for suggestions and are happy to invite as many speakers as the community wants. So I'm going to put that suggestion box in the chat, and please feel free to suggest speakers if you would like. Without further ado, I want to introduce today's speaker. Dr. Bruce Shyu is a professor in the Department of Geosciences at National Taiwan University. His research interests include earthquake geology and neotectonics. We are delighted to have him join us today to discuss the tectonics of Taiwan, the recent earthquakes, and his work on identifying the characteristic offshore active faults in Taiwan. Thank you so much for joining us. And without further ado, the floor is yours.
Okay, thank you. So I'm very happy and I'm very honored to have this opportunity to give this talk. So let me start to share my screen. Okay, so let's start the. Okay, so let's start the slides. Okay, so I'm Bruce Hsu. I'm from the National Taiwan University. So today, as mentioned, I'm going to talk about the seismogenic structure in this very complex subduction collision zone of Taiwan, especially the lessons that we have learned from two recent earthquakes in eastern Taiwan in 2022 and 2024. So I know that not many of you are very familiar with Taiwan. So Taiwan is basically the island in between. We are located between Japan and the Philippines, and we are offshore China. So surrounding Taiwan, we have actually a very complicated tectonic system. So the Philippine Sea plate is moving northwestward toward the Eurasian plate at a rate about something like 80 to 90 millimeters per year. And then that convergence actually making the Philippine Sea plate subducting underneath the Eurasian plate. In the northern part, it's actually along the Ryukyu Trench. And in the southern part, it's along the Philippine Trench. This is relatively normal. However, we actually oh, and by the way, the subduction created uh, the the Ryukyu Island arc and some volcanic island arcs in Japan and the Philippines, as well as the opening of the Okinawa Trough behind the Ryukyu arc. So this part is normal, but actually we on the other side we actually have the South China Sea oceanic lithosphere, which is part of the Eurasian plate, and it's actually subducting eastward underneath the Philippine Sea plate along the Manila Trench over here, and that actually creating some volcanoes, including the Mountain Pinatubo in the Philippines, as well as the Luzon volcanic island arc south of Taiwan. So as you can see, Taiwan is located sort of in between two opposite direction subduction zones. And hence we have a very, very complicated tectonic background. And we also have a very, very active tectonic situation. And because of that, we actually have a lot of active faults and earthquakes. So the largest earthquake that taught us a lot of things, as well as marks the beginning of the earthquake geology research in Taiwan. As some of you may still remember, is the 1999 Chihchi earthquake. The earthquake occurred on land Taiwan in western part of the island, cutting through like a sports field of schools, cutting through rice paddies, cutting through rivers, breaking bridges, roads, and also creating a lot of damages of the houses. And that is actually one of the largest events in the history of Taiwan. And then starting from that earthquake, we start to work on earthquakes, earthquake geology, and active faults. So what did we learn from that Chihchi earthquake? That earthquake occurred in the western central part of Taiwan, and the seismogenic fault is called the Chelongpu fault. And then after the earthquake, we realized that actually not many outcrops of the Chelongpu fault were found before the earthquake. And because of that, people actually didn't pay a lot of attention to that fault. And even the actual exact location of the fault, we were not very familiar with. However, after the earthquake, we start to realize most of the 1990 Chihchi earthquake surface rupture appears to follow some kind of pre-existing topographic features. For example, in this particular photo, the left-hand side and right-hand side are the same. And then you can see that this gray-colored part is the 1999 Chihchi surface rupture. And then this location turn out that is exactly follow a pre-existing topographic scarp, and that topographic scarp is something like 4 to 5 or 6 times height of the 1999 Chihchi surface rupture. But we can even do some kind of very crude estimation that this topographic scarp is probably produced by previous 5 or 6 similar type of event, just like Chihchi. So this kind of situation taught us the significance of using topographic features, not only outcrops, to identify active faults, which is the importance of the tectonic geomorphology. So using this as a background, as a major criteria, we start to work on identifying seismogenic structures all throughout the islands. And then there is a project that funded by our government that we call the Taiwan Earthquake Model Project. And this is a multidisciplinary project with a lot of people working together. And under these projects, we start to working on these active faults and earthquake hazard analysis. And then in 2015, we published our first version of the seismogenic structure map. In that version, we have 38 active seismogenic structures. And then using this information, we reproduced the first version of the probabilistic seismic hazard analysis data results in 2015. As you can see, there are several places that has higher earthquake hazard potentials. And then immediately after we published that, actually after we released this information, but still before the actual publication of this paper, in February 2006, we experienced one major earthquake in southwestern Taiwan, the Mw7.0 earthquake, magnitude 6.6. And that actually occurred in southwestern Taiwan, somewhere over here, create a lot of damages in this part of Taiwan, which is exactly the area that we noticed that has a high seismic hazard potential. And unfortunately, that particular earthquake actually produced a lot of damage in that area, including the collapse of this Weiguan building caused more than 100 casualties, which is very unfortunate. And then 2 years later, in eastern Taiwan, there's a 2018 earthquake, magnitude 6.4, the Hualien earthquake, occurred on one of the structure that we already found that has a high potential to produce earthquake. And then, again, quite unfortunately, that earthquake still caused a lot of damage, and including the collapse of this Yunmen building that caused more than 10 casualties. So these events, although they are very unfortunate, but that also taught us that we are probably on the right track. So using these kind of experiences, we start to work more and trying to refine our seismogenic structure database. And in 2020, we published the second version of the seismogenic structure database of Taiwan. And in this particular database, we refined many of the structures, and then we add 7 additional faults into that database. And using this, together with many other information, we can start to characterize those structures. So just give you some idea of how active the faults are in Taiwan. On the left-hand side, these are the long-term slip rate of the mean long-term slip rate of the faults. At the red color, the blue color are less than 1 millimeter per year. Yellow color are between 1 to 10 millimeters per year, and we actually have several structures that have a slip rate more than 10 millimeters per year. And on the right-hand side are the calculated earthquake recurrence intervals, and then the red ones are less than 500 years. As you can see, many of the structures, many of the faults in Taiwan have earthquake recurrence intervals that are less than 500 years. So Taiwan is really earthquake active, seismically very active. And then using similar data and combined with a lot of other information, we actually come up with the 2020 version of the P-sharp map for Taiwan. And then using this, we actually propose that the southwestern Taiwan again, as well as the eastern Taiwan, are some of the areas that has high earthquake hazard potentials. Okay, so these are what we have done prior to something like 2020. And then, as I mentioned, in 2022 and 2024, we have two recent earthquakes occurred in eastern Taiwan. So what are the lessons that we have learned from those two recent earthquakes? So first, in eastern Taiwan, we actually have a topographic feature called the longitudinal valley that is a linear valley between the central mountain range and the coastal range of Taiwan. And that linear valley actually marks one of the most active regions of the island. Based on some geodetic results, here I use the paper published by Yaru in 2003. We can see that in eastern Taiwan, there is actually up to 4 centimeters per year of the plate convergence actually are absorbed in this very, very narrow valley. So because of that, this is really an tectonically active region. And also because of that, we actually have a lot of major active faults along that valley. So for example, in this figure, you can see that this red line is one of the most primary active faults in Taiwan. We call it the longitudinal valley fault. And these longitudinal valley fault actually are, again, seismically very active. So in the more recent time, we actually have earthquake in 2022, 2003, 1972. And then earlier in the history, we actually have 2 major earthquakes in 1951, October 1951 in the northern part of the valley. And then we also have in the same year, 1 month later, we also have two major earthquakes, a magnitude 7 plus, in the central part of the valley in November 1951. So this is a very active structure. And then other than this structure, as you can see, we actually have this blue line. And this blue line on the western side of the valley, we call it Central Range Fault. And then not only this short, we believe that this structure can extend further to the north, as well as can extend further to the south. Why do we think so? It is because that there are a series of middle-sized earthquakes that occurred along the northern extension of the Central Range Fault in 2019, 21, 22, and an earlier one in 2013. That all along this part of the valley, as well as there is a 2006 magnitude 6.1 in the southern part of the valley that is also along the southern extension of the Central Range Fault. So we believe that that structure, although maybe not as active or not creating bigger magnitude 7 plus earthquakes as the longitudinal valley fault in the east, but still that is also a very seismically active structure. And then the more recent one, the 2022 earthquake, occurred right along this fault. So the September 2022 earthquake series, including one foreshock of magnitude 6.4 and the main shock of magnitude 6.8, occurred right in the central southern part of the valley and along the Central Range Fault. Okay, so let's zoom in to look at this September 2022 Chihshang earthquake series, which occurred somewhere here. And already we can see that an earthquake occurred in an area that we already noticed that we already proposed that could be earthquake, seismic hazard high region. So the two earthquakes, as I mentioned, occurred 1 day apart, one in September 17th, and the main shock occurred on September 18th, the magnitude 6.8. And just judging by the location of the epicenter and the focal mechanisms, people notice that they are occurring on this west-dipping Central Range Fault system on the western side of the valley. But to look more into the detail, we start to look into the central part of the valley, and turn out that there is a very clear surface rupture of the September 2022 earthquake in that region. So if we blow up here, we can see that so there are three lines. Right-hand side is the mapped longitudinal valley fault. Left-hand side is the mapped Central Range Fault. And right in between, there is another line. That line is actually one of the surface rupture of the 1951 earthquake I mentioned just some time ago. During 1951, there is a surface rupture right in the middle, passing the town of Hualien. And because it's right in the middle of the valley, at that time, we didn't know what kind of structure that is. Should that fault belong to the eastern side of the valley, belong to the longitudinal valley fault system, or should this fault belong to the system in the western side of the valley in the Central Range Fault system? We don't really know. However, in 2022, we know, because the surface rupture, which are shown as the blue line, almost right coincident, like perfectly with the surface rupture of the 1951, which is the Hualien fault. And then not only that, in the southern part of the surface rupture, this watermelon field has become one quite famous place to see after the earthquake. You can see very nicely left lateral offset. We also see very, very nicely vertical offset, showing that the western side is moving upward. So this is clearly related to this west dipping reverse fault central range fault system. So after doing some kind of more detailed survey, we can all clearly see that the left lateral offset is something like 1 to 1.5 meter, and the vertical offset is something like 0.5 meter, and then it's all western side up. So that observation clearly tells us that this surface rupture is belong to the west dipping central range fault system. So we can actually come up with some kind of this cartoon figure that we do have a east dipping longitudinal valley fault in eastern part of the valley. We actually have a very complicated system of the west dipping central range fault system. Some of the branches may be daylight somewhere over here, whereas we may have a deeper branches, including this one, producing the surface rupture of the Uri rupture during the 2022 system. So this kind of very complicated system tell us that the central range fault system is actually more complex, more complicated than we previously thought. And then it is, for us, it tells us that there is a need to characterize such a complicated fault system to try to adjust for example, their slip rates, their earthquake recurrence interval, and then based on a lot of observations, how we characterize these kind of complicated fault systems. And more importantly, very interestingly, that we actually have some very minor ruptures also on the east dipping longitudinal valley fault system. For example, you can see some small like bumping here. There's basically a small surface rupture on the longitudinal valley fault. And then in the central part of the valley, we also have this kind of very small, something like less than 10 centimeter surface rupture along the longitudinal valley fault. And then turn out if we do some kind of co-seismic slip distribution modeling, we found that whereas most of the energy was released on the central range fault system, there is actually some small part of the energy that is also released by the movement on the longitudinal valley fault, the east dipping longitudinal valley fault. And then if we calculate the co-seismic Coulomb stress change, we also see that the earthquake actually some sort of have rupture on one fault, on the western side fault, actually have some kind of negative impact on the fault section on the opposite fault. So it means that because these two faults are so close to each other, they actually have a very close interaction between each other. And then if we put all of the historical record there, we start to realize that in centennial timescale, there is actually a complicated interaction between the two fault systems. So, for example, earlier in the 20th century, we actually have some larger event on the central range fault system, and then after those systems, we actually have after those earthquake events, we actually have a short period of time of the quiescence on the longitudinal valley fault until 1951. And then, as I mentioned earlier, 1951 earthquake series, 2 magnitude 7 plus in the northern part of the valley, and then 2 magnitude 7 plus in the southern part of the valley, produce a big earthquake episodes on the longitudinal valley fault, and that actually create a longer time of quiescence on the central range fault system until more recently in the 2020, uh, well, before 2020 and after 2020, more recently, we actually start to see a bunch of events on the central range fault system. So basically, we can see that in the millennial time scale, centennial time scale, we can see that these two earthquakes actually have some kind of alternating earthquake sequences between the two systems. So that actually also produced a big challenge for us because we need to identify and try to calculate such kind of interaction between the two or even more fault systems in terms of trying to calculate the future earthquake potentials. So from the 2022 earthquake, we start to learn that there is a possibility that some fault systems are interacting with each other very complicatedly. We, of course, in seismic hazard analysis, we start to calculate and consider multiple fault rupture earthquakes. But in this kind of complicated interaction between structures, we still have a very, very hard time to do the right estimation and calculation, and that will become one of the primary lesson in the future. Okay, so that's 2022 earthquake, which is more or less on land. And then later, 2 years later, in last year, in 2024, we had another earthquake in eastern Taiwan, the magnitude 7.2 Hualien earthquake in the northern part of the valley. And this earthquake, the location, the epicenter location is almost right on the coast. And then the earthquake focal mechanism also tell us that it is possible the earthquake is possible to occur on either a west dipping plane or a east dipping plane. So at some time there is a big debate on whether it was produced by the east dipping longitudinal valley fault system or something further to the east that is west dipping. However, if right after the earthquake, we go to the Hualien area, and then at the Hualien harbor, we found that there is actually a co-seismic coastal uplift of about 0.5 meter that is very, very clearly shown by this uplifted oyster layer. So there is co-seismic coastal uplift, and also there is some kind of local witness account that telling us there is a small but clear tsunami event with a run-up height of something like 1 to 2 meters. 0.5 to 1 meter right after the earthquake. So I think it is more likely that we may have a structures that is offshore. If we go back to this kind of figure, you start to realize that our previous effort only focus on land part of Taiwan. How about offshore? We actually haven't identified any offshore active structures. However, if we only look at the on-land structures, and if we add all of the slip rate of these on-land structures, we actually get a convergence rate across the land area of Taiwan of about only 6 to 7 centimeter per year. As I mentioned, the plate convergence is up to 8 to 9 centimeter per year. So there is actually a 20 millimeter per year of plate convergence actually is missing. So it is very, very likely, very, very possible that we do have offshore active fault, offshore seismogenic structure that we haven't identified because we only focus on the land. So how do we do that? So actually, more recently, my student and I are trying to using multiple data, many previous published data, including geophysical, seismic reflections, and all kinds of survey data, try to identify offshore seismogenic structures. And then using some kind of criteria, first, we need to make sure that the fault, the disturbance has to be shown on the seabed structure, seabed layers in seismic profile. And also, we need to see this kind of linear feature of faults in the bathymetry map that is continuous and also longer than 20 kilometers. Using this kind of criteria, now we have starts to produce the very first version of offshore seismogenic structure database. As you can see, on land, we now only have 45 seismogenic structure active faults. Offshore, right now, we have identified more than 50. So clearly, there are a lot of things going on in the offshore region. And then this structural database, if we focus in the more or less related to the subduction zone part, in the northeastern part of Taiwan, we actually have various structures related to the Okinawa Trough and also related to some normal faulting in offshore northwestern Taiwan. And then in the hanging wall part of the Ryukyu subduction zone, we actually have a series of structures, including two major right lateral faults that actually cutting across the subduction complex. And then in the southwestern part of Taiwan, on the hanging wall of the Manila Trench, we also have a series of reverse faults together with the folding is creating some sort of a fold and thrust belt southwestern Taiwan. So if we put all of these together, we actually can see that the characteristics of these offshore structures also is consistent with the tectonic development of Taiwan. In the southern part of Taiwan, when the collision has yet started, we actually have a lot of reverse faults. And in the central part of Taiwan, and also in the northern part of Taiwan, the collision has already ended. In the post-collision part, we actually have a lot of normal faults, and then we have strike slip faults in between. So using a lot of information, like I said, we can use a lot of geophysical data and also the seismic reflections. We can construct the structural geometry of these offshore structures. And then using this structural geometry, we can start to calculate the earthquake magnitude, the magnitude of earthquake that these structures may produce. And then if we consider multiple fault rupture scenarios, we can see that first, almost all of the structures are capable of producing earthquake magnitude more than 6.5. And then if we consider multiple fault rupture scenarios, we actually have structures that can produce earthquake up to 7.5 or even larger. So clearly, these structures are posing significant earthquake hazard for Taiwan. And then if we put all of this information together, the larger magnitude, which means that the displacement per event will be higher. So we can put all of these structures with different thickness of the lines to represent the displacement per event. As we can see that there are a lot of offshore structures, especially in eastern Taiwan, may have a displacement more than 5 meters or more during one earthquake event. That actually has a lot of implications for that. And then if we want to do more, we have to calculate the slip rate of these structures. As you can see, offshore structures, we cannot go to the field. So we have to use a lot of innovative way to do the slip rate calculation. Here I'm just going to show a couple of examples. Like in the northeastern part of Taiwan, those normal faults, we can actually use some kind of very early sequence boundary that show up in the seismic reflection lines. And then if we use that to calculate, use these time of the propagation of these kind of normal fault activation to calculate these, we can actually use the total offset divided by the timing of the activation of the normal faulting regime. We can actually get some kind of slip rate between, well, very huge uncertainty, slip rate between 0.1 to something like 7 millimeters per year. In domain B, is the Okinawa trough. We can use similar method if we know some of the reflectors, the age of the reflectors, their offset, and then we can calculate the slip rate to something like 1 to 3 millimeters per year. And then in other places, if we know, we have some idea of the subsidence rate, and then across a structure, if we have a difference of the subsidence rate, we can also use that difference to have some idea of the possible slip rate. And that actually tells us that it's also something between 1 to 3 millimeters per year. So using this kind of information, we can come up with a lot of information of the slip rate. However, as many of you know, that in the hanging wall of the subduction zone, the material is actually quite soft. So those total slip probably are not entirely accumulated and released in earthquake event. So we have to calculate something. And then in the hanging wall of the Ryukyu Trench, we actually use some kind of even more innovative way, is that we use the plate convergence rate, and then the subduction, well, the plate convergence direction and the subduction direction, and using this kind of triangle calculation, and then we can come up with a slip rate of those major right lateral strike slip faults with a slip rate something between 30 to 70 millimeter per year. A very huge number, right? So as I mentioned, that we have to consider the coupling ratio of this area, and then the previous published coupling ratio have some kind of number, and using that, we can come up with a adjusted slip rate of those faults with a slip rate of something like 5 to 30 millimeters per year. Still very large, but I think that's more realistic. So using all of this information, we actually can construct a offshore seismogenic structure database with all of the information, geometry, earthquake magnitude, slip rates, as well as the earthquake recurrence interval. And then here, using this slip rate, you can see that we have the domain C, the hanging wall of the Ryukyu subduction system. We actually have a very high slip rate structures, although their uncertainty is also the highest. And then using those information, we can compare that in the offshore eastern Taiwan, we actually have much lower slip rate for those normal faults. And then with this earthquake magnitude and slip rate, we can actually calculate the earthquake recurrence interval, and turn out that the earthquake recurrence interval are usually on the 1,000-year time scale. However, for the domain C in the Ryukyu subduction zone, we actually have very, very short earthquake recurrence interval. Okay, so we can see that this kind of information may have a lot of possible applications. Earth seismic hazard analysis, for sure. We can also have some kind of information, maybe, for example, right after an earthquake occurred offshore, if we can quickly figure out that, for example, like in 2024 earthquake, the earthquake occurred somewhere over here. And then if we can know, if we can try to connect this earthquake with our mapped offshore structures, and then if we have some idea about how large the slip per event of those structures may be, maybe we can have a quick understanding of the tsunami potential that may be created by this kind of earthquake. In fact, that earthquake did have a tsunami warning for the southern part of the Ryukyu Islands in Japan. The actual tsunami wave height is not very high. Okay, so I think I have used a lot of my time. So let me start to wrap up things and start to summarize a lot of things. So basically, starting in 1999, the Chi earthquake, which is already more than a quarter century ago. So we have started to learn a lot of lessons, how to use geomorphology to identify active faults and how to characterize those faults. And then using those lessons, we have used the on-land seismogenic structure database for Taiwan. In 2020, we published these with 45 structures. And then in using this kind of information, we can calculate the Isha of Taiwan, the probability seismic hazard analysis for Taiwan. And then more recently, in 2022 and in 2022, earthquake occurred in longitudinal valley in eastern Taiwan. And then from that earthquake, we start to learn that there is a possibility that some fault systems may have very close and complicated interactions. So we need to identify and characterize these kind of complex fault systems and try to understand the interaction between these complicated fault systems. And then more recently, in 2024, Hualien earthquake tells us that there is a very possible potential that we have more structures in the offshore area of Taiwan. And then due to using this kind of lesson, my students and I have started to identify and characterize the offshore active fault, offshore active structures. And then in the future, we are going to utilize these new data sets for the next generation of seismic hazard analysis. So after more than a quarter century after the Chi earthquake, we have learned a lot of things. And then we also have learned a lot of things from the recent earthquakes that we start to realize that we still have a lot of things to do. So in the future, let's work together toward a better understanding of these important issues for many, many different places in the world that has this kind of future earthquake hazard potentials and for the future earthquake hazard preventions. With that, I thank you very much, and I'm happy to answer your questions.
Thank you so much for that amazing talk. I want everyone to know that the chat and the Q&A features are both available to ask your questions. I'll give everyone a few minutes to type anything they might have. Okay, well, I'm not seeing any questions at the moment.
Mm-hmm.
So I just want to remind everyone that if they think of a question after, or if for those of you who might be watching this asynchronously once it's uploaded on the YouTube channel, if you have any questions for Dr. Xu, please email us and we will make sure to get it to him. And Dr. Xu, thank you again so much for that
Yeah.
fantastic talk and for
Thank
taking the
you.
time. We really appreciate it.
Thank
Thank
you.
you all,
Yeah.
and have a great rest of your evening or
Yeah. Or
morning.
morning or afternoon or whatever. And yeah. Yeah. Thank
Thank
you.
you very much.
Yeah. Thank you. Bye.
Bye, everybody.